Now our topic is potential energy of a dipoles in a uniform electric field. What will be in this topic? We will cover the formula for the potential energy and the stable equilibrium position and unstable equilibrium position. Let us start. This is our uniform electric fields. Now a dipole. This is the minus q plus q. This system is a dipoles. I have rotated this dipoles from an angle theta with the electric fields. Now in these positions, the dipoles on this dipoles acting two forces. One is QA along the direction of electric fields. Another is minus Q in the direction which is just opposite of the electric fields. These two forces equal, which is in equal magnitude but in opposite directions, make a couple. One force is along this one, other force is along this one. They are anti-parallel, so they can rotate the dipoles in the direction of stable equilibrium position. Let us go at this position. There is a torque tau. It has a tendency to rotate the dipoles in the clockwise directions. Now further, if I rotate this dipoles from this position, making an small angle d theta, okay, from this position to this position, just I have rotated at this state an angle d theta from the direction of dipole moment. Now for doing this, we have to do some work against the torque. Against the torque, our torque is in clockwise directions. You are rotating the dipole in the anti-clockwise direction. So in this case, we have to do some work done. The small work done of rotating these dipoles in anti-clockwise direction will be like in translational motions. The total work done is equal to linear force multiplied the displacement. In rotational system, we have force replaced by the moment of force, that is the torque, and the displacement would replace by the angular displacement. Now if I place the value of P in this case, now it becomes P sin theta d theta. If I say that if the dipoles is starting from this position, suppose this is theta 1, from this to this, now it has an angle theta 2 with the direction of the electric field. We have to do a total work done of rotating this dipoles from an angle theta 1, from the angle theta 1 with the direction of the electric fields to theta 2. So we have to integrate this one. In integration, we are using to add small quantities of the work done. Now P is constant taken out, and integration of sin theta will be minus cos theta, lower limit theta 1, upper limit theta 2. Your upper limit is theta 2. If I take minuses outside, minus P, now cos theta, lower limit theta 1. With the help of this definite integration, upper limit, first put the upper limit, which is theta cos theta 2 minus lower limit cos theta 1. Now this is our formula of rotating the dipoles from theta 1, from the initial angle theta 1 to some another angle theta 2. Now if I generalize, if any dipole is placed in the normal direction, minus q and plus q, and electric field is along this one, if the angle between them is 90 degree, so in that case, in this position, the dipole has no potential energy. So now if I goes, if our initial position 90 degree, if I say theta 2 comes out theta, so now cos theta replaced by cos 90 degree. Now we know that in cos 90 degree it comes out 0. If all place these values in equation number this, Now the total work done comes out minus P cos theta 2 replaced with theta minus cos 90 degree. Cos 90 degree comes out 0 degree. Now finally we have the value minus P cos theta. If I use P, dipole moment is a vector quantity, and in the scalar dot product, simply dot product, I can represent is like minus vector P dot T. Minus P dot T. Now this work done is stored as a potential energy. Now we can say that it is a potential energy of these dipoles in a uniform electric field. So our potential energy becomes, when the dipoles makes an angle theta, suppose in this position it makes an angle theta with the direction of the fields, our potential energy will be minus P dot T. We can utilize this. Now in which positions dipole has stable equilibriums, or I say that minimum potential energy, and unstable equilibrium maximum potential energy. We know that the formula is minus P cos theta. If the angle theta is equal to 0 degree, I have the minimum potential energy. U minimum is equal to minus P cos 0 degree. Cos 0 degree has the value minus P. Now since energies can be positive, negative and 0, so this will be our minimum potential energy. This minimum potential energy will be our stable equilibrium position. Stable equilibrium position. Another position, when the dipole has the maximum potential energy. When the dipole has maximum potential, it means that when theta is equal to minus 5, and if I place these values in this one, in this formula, so we got maximum potential which is minus P, theta replaced by pi, cos pi at the value minus 1. Now it comes out minus P and cos pi at the value minus 1. Now it becomes P. This is the positive value which comes out maximum. It means that when the electric field is along this one and your dipole moment is along this one, dipole moment and E is anti-parallel, in that case it is unstable equilibrium. Means minus Q this side and plus Q this side. So dipole axis will be along this one. In that case it will be maximum potential energy. Maximum potential energy will be unstable equilibrium. Dipoles remain in this position, but if you disturb this one, dipole remain in this position. If you disturb the dipoles from this position, either in upward direction or downward direction, it will not come back in this position again. It will go somewhere. It will go in the stable equilibrium position. That's why we call this as unstable equilibrium position. Any equilibrium, whether it is stable equilibrium or unstable equilibrium, the total torque and force should be 0. Now the torque in that case will be, you know that torque is equal to P sin theta. Our angle is at unstable equilibrium is pi. Now cos pi has the value 0, the torque comes out 0. Same way, in a stable equilibrium position, your angle is theta. Here place this one theta. Now torque comes out minus, not minus, this is P sin 0 degree. P sin 0 also 0. So in any case, whether it is stable equilibrium position or unstable equilibrium position, our net torque comes out 0. So any torque, any dipoles has the tendency to come in the stable equilibrium position. Now it means that when your electric field is along this one, the dipole should have the directions, the dipole moment along the direction of the electric field. Now, so whenever axis of the dipole and electric field in the same directions, in that case you will be in the stable equilibrium position and your potential energy will be minimum. The minimum value becomes minus P. So, so these are the two cases. Now third case will be this one. When the dipoles, in that case your potential energy will be 0. Potential energy could be also 0 whenever angle between electric fields and dipole moment is equal to 90 degree. Now your potential energy in that case P cos 90 will be 0. Now your potential energy will be 0. These are the three situations in which dipoles can remain.